Welcome to an Ultralight Airplane Workshop testing, tools, and structural analysis video. In this video, we're going to talk about determining the loads, how to distribute the loads, and applying loads using our Whipple Tree for the nose rib of the UWS-4 Ultralight airplane. Now you could use the word Whipple Tree or Whipple Tree. Doing internet searches, I found out that Whipple Tree with two P's brings up more results than Whiffle Tree, so I'm going to be using Whipple Tree. So a Whipple Tree is a tree structure of load spreaders. So you can take a single point load and spread it down to multiple loads, and you can adjust how much load each of those individual loads get. So in this video, we're first going to go back to the office, and I'll use the computer to show the structure of a Whipple Tree. I'll show how to do the calculations to get the load you want from the Whipple Tree. And then we'll come back out to the shop and we'll actually build one for testing nose rib on the UWS-4. Now the actual testing of the rib will be on another video. And in particular, this Whipple Tree will be used in testing the Truss Style Nose Rib. And near the end of the video where I talk a little bit more about using it for testing, I'll put a link to the playlist for testing that nose rib. So let's go back to the office and get started. Now we're back in the office. Let's talk about what we're going to do here. Now first, we're going to go over what a Whipple Tree is, a little bit more on that. Then I'm going to go over how I did calculations for the Whipple Tree I'm going to build so I know how the load is going to be spread the way I want it to be spread. And then with those calculations, we'll be able to go back out into the shop and we're going to build it. Now let's go over the arrangement of the Whipple Tree, the component we want to test with the load, and how we're going to make that load and how we're going to read the load. So down here on the bottom is the thing we're going to test. So this could be something like a wing. So we'd have some portion of the component is going to be fixed. And that's what this represents over here. We got a fixed point, so this doesn't move. Then we got our Whipple Tree here. Now I've only got 3 load spreaders here with 4 load attach points. Now typically, like on a wing, you want to have quite a few more, probably 1 at each rib. Then the Whipple Tree is attached to something to measure the load. Now I'll have a 500-pound load cell that I'm going to use when I'm testing this nose rib. Now I've got a display so I can see how much load there is. And then I'm going to use a hand-actuated or pumped hydraulic ram that'll be attached to a gantry or something like that that I can pull on with the hydraulic ram. That hydraulic ram will then apply the load to the cell applies it to the Whipple Tree, and then the Whipple Tree applies loads to our wing or whatever it is we're testing. Now, as was probably evident from the previous picture, this Whipple Tree takes a single load, total load that I'm applying, and then it starts distributing it down, and it distributes it to multiple points on the item that we're going to test, in this case, a nose rib. Now, for this nose rib, my fixed points are over here. I'm going to have 2 fixed points, which is very similar to what our spar would be like. So we'd have an upper spar cap, a lower spar cap, and there'd also be a web in here that the rib will attach to, but I didn't represent it here. Now what's really cool about the Whipple Tree is that we can apply different loads at each point down here on our component. We can design these load spreaders to give the exact load that we want. So that's the challenge we have, is do the calculations to figure out where all these various load locations are. For example, there's going to be, in this case, a wire coming down here from each of these holes here in this load spreader. In fact, all these level 1 load spreaders down here, down to a rivet location on the rib. But then it attaches to another load spreader, so I got to calculate those hole positions. Now these will be bolt holes so that this can swing. And then of course the level 3 and then level 4 load spreader. So what we need to calculate is the distance between these holes and the position of the next load up position. Now, load spreaders either have 2 points or 3 points. So, for example, all these down here, there are 2 load points down here, and then a transfer point up to the next level, there's 1 for that. So here we have left and right, and so that's only 2 dimensions. If we had a 3rd dimension, there'd be 1 either in or out of the screen. Here would be the 3rd one. Now, I have calculated how much load I want to have on each rivet location on my nose rib. So all these load locations down here, at all these holes down here on level 1, I know. What I don't know yet is where should this hole be going up to give me the correct load distribution that I want. And so the way we're going to do these calculations is with a moment. And you may remember some videos we had in the past that a moment is a load times a distance, or an arm. And so for at least this page, L is going to represent loads, and this X is going to represent some distance from a reference point. And then M is our moment. Okay, so let's look at this in the graph, or at least what it would look like on the load spreader. So we have two loads coming down on the ends of our load spreader. We already know those. Those are our rivet locations. And we know our X1 and X2. Now it's going to be the distance of that rib in the X direction, at least along the chord line, from a reference point. And that's going to be the leading edge. So as an example, I know that very first rivet is 0.44 inches from the leading edge. So what I don't know yet is where should I apply a load along that spreader to give the correct load at these points? Well, we know a few things. We know that the load pulling up at that single point is the sum of these other two loads. So load at 0.3, that's up in here, is the sum of the load at 0.1 and 0.2, the sum of these two loads here. So we got a moment arm here at 0.1 and a moment arm here at 0.2. So we can calculate those. That's pretty easy. So X, that distance for the rivet, times the load. That gives us our moment arm here at 0.1 and at 0.2. So that's what these two equations are here. So now I can sum up those two moments. And I happen to know that the sum of these two moments has to equal the moment here at 0.3. So now I can do the calculations to get that moment at 0.3. Now that I know what the moment at 0.3 and I know the load at 0.3, I can calculate the X distance. So that's just undoing the moment arm calculation. From over here, just rearranging it for the X. So take our total moment that we just calculated, divide by that total load, and that gives us our X location. So we can do that calculation for each one of these load spreaders down here. Now you'll notice I have an odd number of rivet locations. So this last one back here, it could be any of them that we do this to, but this last one I'm going to move up to the next tier up. Well, now that we know the moment at each of these position 3 holes on all of tier 1, now we can calculate the load spread on tier 2. Just go through the same thing. We know the X at each of these holes now. We know the load at each of these holes. Knowing that, we can calculate position and load of the next load positions going up. And we just do that all the way up. So that's all we're going to do. Now, there may be a lot of calculations to do it, but that's where a spreadsheet comes in pretty handy. So real quick, let's just go look at the spreadsheet that I use to do the calculations here on this nose rib. Actually, real quick before we do that, let's go take a quick back and I'll do a really fast high-level view of how I calculated the load on each of the rivets for that nose rib. Now I have an approximation for the load distribution on the chord of the wing at the root of the UWS-4 Ultralight airplane. And I've got two conditions, one at a low speed, high angle attack, that's this blue one here, and the other one is with the flaps deflected, and that's this red one here. So you can see at the high angle of attack, this blue one has more load here up here on the nose rib. And by the way, this is the wing chord here on this x-axis. This is the pressure in pounds per square foot up here on the y-axis. Well, knowing that pressure calculation up in here, knowing the distance between the ribs, in this case that's 14 inches, and knowing the rivet locations and distance between rivets, I can calculate the load on each of the rivets. And that's what I've done up here. So I have 11 rivets up there on the nose. I know the rivet locations, so that's what I was just talking about previously. That first rivet is at 0.44, and then I know what the rivet location is for each of the rivets from the leading edge. And then this column right here, that's the calculated load on each rivet. So maximum load we have is about 11.4 pounds. Minimum load we have is near the spar, 2.2. So now that I know the load on each rivet, I know each rivet location, we can start calculating the spreaders. So these are my spreader calculations. So this area right over in here, this is again just entering the X location of my rivets. That's these numbers here, and the load on each rivet, and that's these numbers here. And then I calculated the arm for each one of those. So that was the first step that we need to do, is calculate the arm at each of those rivet locations. So then I come up to tier 1 up in here. So I calculate the load that that tier is going to pull. So that's the two rivet loads together near the nose. So that's 17.5 pounds. And so I did that for each load spreader moving back toward the spar, except for this last one here. He's by himself. I'm going to move him up to the next tier. And we can calculate that arm at the top of the load spreader. That's just summing these two arms together. That's this column right here. Now that we have the total load and the arm, we can calculate the X position for that top location in the tier 1. And that's this here. So that top location is going to be 1.065 inches from the leading edge. Now, to make it a little bit easier for me to fabricate these load spreaders, I'm going to put the most forward hole, I'm going to call it location 0. And then I did some calculations to say, well, that hole on the top, location 3, is a certain distance after that. And then location 2, the one that's farthest back, I want to know how far back it is also from that first hole in the leading edge. So I did that for each of the load spreaders. So for example, so this would be 0 location for this specific load spreader. And then the second number we were just looking at is this top hole. And the third number we were looking at is this one back here. And then I did that individually for each of these load spreaders. So as you can see, for the second load spreader back, forward hole 0, the lifting hole, how far back it is from that 0, and then the aft hole, how far back it is from that leading edge. So I did that for all these load spreaders. And then I just basically duplicated this information. So here's the level 2 load spreader, level 3 load spreader, and then the top load spreader. And then I do some calculations to do sanity check, make sure I haven't made any mistakes. The load coming all the way up through here at each tier, the sum should always be the same. So let's go back and see what it was from my nose rib calculations. So I've got that number here. So that total load on the rib is 87.7 pounds. So that's this number here. So back here on these load calculations, let's start at the very beginning. So 87.4. So that's what, 0.3 pounds lower. So there's some round off error. That's fine. 0.3 pounds is nothing. So let's look at the tier 1 sum. That's 87.4. That's correct. Tier 2 sum, 87.4. Correct. Tier 3, 87.4. And then the very top center load is 87.4. So I did a little quick sanity check, make sure I didn't have any mistakes in my formulas. So that all adds up. And then one more quick sanity check. This location here, 7 inches from the leading edge, which is that top hole. So this hole right here, it should be 7 inches back from the leading edge. So let's do a quick think on how close that is to being correct. So here's that load chart again. Now the spar is back here. Now this is inches down here, and the spar is about 19 inches. So that's right around in here. So that's awfully close to being triangular shaped with a little bit of extra offset, lifting it up a little bit higher. Now, if it was strictly triangular shaped, let's say it came down to 0 here at 19 inches and then came up, then I know that that load centroid would be 1/3 back. So a little over 6 inches, about 6 1/3 inches, about 6.5 inches back from the leading edge if this was strictly triangular shape and didn't have this extra little bit down here. But this little extra bit down here, let's consider it by itself. So the centroid of that, which would be rectangular shape, would be right in the middle. So that would be at about 9.5 inches. So I know that lift centroid has to be somewhere between 6.5 and 9 inches. Now I also noticed that the area here under this triangle is going to be much larger than the area down here for this little rectangular area. So that means it's going to trend closer to the triangular centroid. So it should be closer to 6.5 inches than it is to 9.5 inches. Now we said it was 7 inches in our final calculation. So we're at least in the correct ballpark. So we did a little sanity check. The numbers aren't completely out of whack. We got all of our calculations for all these numbers for the holes. So the next thing I could do to make it a little bit easier for me is to draw this up on CAD. I don't really need to. I can just write this down on a sheet and go out and fabricate it. But it'd be nice to have this on a sheet, help kind of keep track of where I'm going, or at least reduce the possibility of having mistakes. And so here you can see where I put all that information into FreeCAD. And in fact, this drawing that I put here into FreeCAD is what I used to make that chart. So I used FreeCAD to make some technical drawings of all the parts. So here's the total assembly. and I put names on each of the parts. So it's spreader 1-1, so that's level 1, number 1, 1-2, 1-3, 1-5, etc. Then on spreader level 2, that's 2-1, -2, and -3. And then spreader level 3, and there's only one of those, and spreader 4. And then I've got these ties along here. Now, I have identical ties on a lot of these, and I have two ties that are kind of unique, which is tie 2 and tie 3. And tie 4, of course, which goes up to the shackle that goes to the load cell. So here's all the load spreaders for tier 1. And again, you can see those distances I came up with before. So this corner here, this hole here is going to be 0. And then I calculate the distance, the X distance, to the load hole, the top load hole, and the distance to the aft load hole. And so I did that for all of these. So here's the tier 2 spreaders. There's only 3 of those. And this is tier 3 and tier 4 together. And tier 4 is only at half scale. And then these are the various ties that I have. So I'm going to have a whole bunch of these tie 1s, and then one tie 2, one tie 3, and one tie 4. So I'll print these out and take them out the shop. And we'll start fabricating. Well, for the last few videos on these areas, on these sections of videos where I'm fast forward through some operations, I did some text overlay to try to explain them. In this video, though, I'm going to do a voice overlay. We'll see how that goes. And keep in mind, when I'm showing how I'm going through various operations to make something, I'm not necessarily showing every single step. There's going to be some steps I leave out, either because they're not important, they're boring, or when I recorded them, I was in the way, so you couldn't really see what was going on. So just because I'm not showing something doesn't mean it didn't happen. So what I'm doing here is I'm marking out the widths and the lengths for the spreaders. It would have been faster to use some rectangular bar that was the correct width, and all I had to do is cut out the lengths. But I happen to have this scrap aluminum hanging around. It was the right thickness, which is 100 thousandths of an inch thick. So I'm going to go ahead and use it. And you'll notice this paper here to the right of the screen. I have the dimensions for the hole placements, the lengths, the widths, all written down here on these pieces of paper, and I'm referring to those as I'm trying to mark down the dimensions for the spreaders on this aluminum. Next thing we'll do after I get this done is we'll cut it out on the bandsaw. As you can see, I'm using a bandsaw to cut out these load spreaders. I set up the lines so that if I cut in the middle of these lines, the length of the load spreaders would be right. And in this case, right would be 1 3/4 inches. I kind of picked that value somewhat arbitrarily. I didn't actually do a structural analysis to come up with it, but it looked about right. As I mentioned before, these load spreaders are being made in pairs, and they'll sandwich the load ties that are vertical. Now you notice I've written some numbers on these. That's so that I can keep the pairs together. There's an A side and a B side. And the reason I've written numbers on them is for some of these load spreaders, the hole positions are going to be fairly similar, and so in order to tell them apart, I've written on them. Well, next I made the vertical ties to tie one tier of load spreaders to the next upper tier. Now most of these ties only go one tier. I wanted the load spreaders to be 100 thousandths thick, but I wanted these vertical ties to be 125 thousandths thick, and I didn't have any of that, so I had to go buy some rectangular stock. So almost all the vertical ties are 1 inch wide stock, except for the very top one. I have to have a much larger hole in it because I'm going to put a 1/2 inch shackle through it, and so I use 2 inch wide stock for that. So I marked them up just like I did the load spreaders, and then again, like with the load spreaders, I cut them out on the bandsaw. I'm using a disc sander, 80 grit disc sander, to remove the burrs that were put onto the load spreaders on the bandsaw. And for safety reasons, I'm rounding the corners on these load spreaders. So I happen to have a catastrophic failure while doing load testing, and parts of these load spreaders go flying. With these rounding corners, I'm either less likely to get injured or reduce injuries that do happen. And I'm just kind of eyeballing these corners. The radius is roughly 1/4 of an inch. It doesn't have to be exact, just get them rounded off a bit. And these pieces of aluminum can get hot while I'm running them up against the disc sander and the belt sander. So I've got a little pan of water here that I cool them off with as I'm doing the sanding. Now for these load ties, the pieces of metal that connect the various stringer levels together, my initial thought was just to use this sander, again, just round off these corners, but I was going to go up to a 1/2 inch radius instead of 1/4 inch radius. Well, with the bigger radius and the thicker material, this is 125 thousandths, they were getting really hot fast, and it was taking a long time. So I finally gave up on that, went over to the bandsaw and cut the corners off. And then after I cut the corners off, I went back to the sander and just finished sanding them off. And again, I was just eyeballing this. I didn't do a very good job. I really didn't need to make the radius quite as big as I did for most of the situations. It was just the level 1, very short ones that I need to do it, because the ties from the top of the load spreader could possibly interfere with ties from the lower end of the load spreader, just because the corners were too close together. I didn't have to make these radiuses quite as large as I did. And next I used the belt sander to clean up the edges that were cut on the bandsaw, and to clean up the corners just a little bit more. Then I went and cut out the last tie, which connects the Whipple Tree to the load cell. And it's got that bigger hole in it. So I cut it out, and then I also then cleaned up the edges on it. And now we get the chance to start drilling holes. To start, we're going to drill holes in the ties that transfer load from one tier of load spreaders to the next tier of load spreaders. And there's one hole in each end. Not too big a deal. They don't have to be super accurate, but I am going to make it accurate anyway. I'm going to drill these holes 1/2 of an inch from the end on each end. And I got a little jig here to help me do that. Now, I can't really eyeball where to put these holes. First, these load spreaders are each in pairs, and so the holes have to line up exactly right so I can get bolts through them. And then number 2, those holes have to be in the right distance from each other in order to get the load spread correctly. So I'm going to use my vertical mill here and the table on it in order to get those holes in the right position. But first, we're going to drill the hole that all the load spreaders have in common. So the most forward hole, the way I've designed this, the most forward hole is in the same spot on all these load spreaders, and that's 3/8 of an inch from the end edge and the bottom edge. So first we're going to drill all of those. Now I put a jig here on the table in order to get those spreaders in the correct position for the hole. So all I have to do is press the load spreader up into the jig and then hold it in place to drill the hole. So this is a pretty fast operation. It's time to drill the second hole in the load spreaders. Now this is going to be the second hole at the bottom of the spreaders after the first hole that we drilled. And I'm calling this position number 2. At least it's position number 2 in the spreadsheets and the diagrams I've made. So this hole is going to be a different spot for each pair of spreaders, just because that's how it worked out. Now I'm going to use the same fixture that I was just using for the first hole. So I'll put a bolt through that hole that I just drilled in the spreaders and through that same hole in the fixture in order to hold the spreader in the right spot. And then I'm going to crank this table in the X direction over to where I need to drill the second hole. Now you can't see it here, but the crank has a mark every 1/1000th of an inch. So I just need to know how far to crank it around, how many times around. One complete revolution of the crank is 1/100th of an inch. So I need to know how many hundredths I need to crank over, and then how much of a portion of crank that I need to rotate to get to that second hole. And now it's time to drill that top hole in our load spreaders. So just to keep from getting lost here in the x-axis, I'm going to go way back to the beginning near that first hole we drilled, just to make sure I know where I'm at. Then what I'm going to do is I'm going to change the y-axis on the table. So that means I'm going to move it just enough to get to where I need to have the correct height for that hole. At least height when it's upright. Right now it's laying on its side. Now I have a little problem here. The place where I'm going to drill this top hole is right over one of the supports on the bed of the table. So if I drill too far, I'll drill into my table. I don't want to do that. So I'm going to go just a little bit farther past the top of the load spreader and then figure out how far down I have to drill to get through the material. And then there's a dial on my quill of my mill that I can move to indicate how far I've drilled down to keep from drilling down too far. Then we go back to the correct Y position. We still haven't got the correct X position. So now we move the X position of the table over to where we need it.
So we're ½ inch.
And then we just drill the hole and just make sure we don't go too deep.
4, 5, 6.
Then we just repeat this process for the other load spreaders.
Perfect. Okay.
Well, it's finally time to start assembling the Whipple Tree. So the way I'm going to do this, and it really doesn't make that much difference, but I decided it'd be a little easier handling to first do the vertical load ties on each pair of load spreaders. So I did that first. And then I assembled the load spreaders together. And these load spreaders and the load ties have to swing fairly freely. So the way I did that is I tightened up the nuts on the bolts all the way and I backed it off about 1/4 of a turn. And that was just enough freedom of movement that I don't think will have any binding issues. But it's not so loose that it just flops around. Well, we've come to the last little bit of assembly for the Whipple Tree. And that is to add some wire hangers from the tier 1, the bottom tier of the Whipple Tree, that will hang down and hook onto some fixtures that I will rivet to the skin of our rib test fixture. They'll essentially be the same kind of attachments that I used in the cantilever rib test, where I tied some string to some fixtures that had been riveted to the skin, and then I hung some weights from those strings. So the fixtures will be roughly the same. Well, we're just about to the point where we can do some testing, or actually I shouldn't say that because there is more stuff that we need to do beforehand. But we're pretty close on the Whipple Tree. So I mentioned before a fixture that I was going to tie these wires to here, these load wires. So this is what I'm going to rivet to the skin of my rib fixture. So we'll just put a hook down here in this wire. We'll bring it around and probably do a little twist on it to hold it. And we'll do that at each rivet location. So basically, this form will have a bunch of these riveted along here at each rivet location to apply a load at that rivet. As I mentioned, there are a few more things we need to do before we can do our testing. I need to finish forming my rib. So I need to make a 90-degree bend here on this flange that the rivets go into from the skin. And I think I'll probably make a video about that because they're going to make a little tool to help do that bend. And then I'm going to have to make a fixture to hold this in place. And it'll hold this in place on a larger fixture, which I'm going to build. I think I'll make it out of wood. And it is going to hold the top of the hydraulic ram. And then at the bottom of the fixture, whatever I have holding this will be bolted on. And so that will let me pull the load on the Whipple Tree to do our load testing. So there's a little more I still need to build. I'll probably do a video on finishing the rib, and I'll do a build on finishing the structure for doing the load testing that all this will go into. And then we'll finally get around to pulling a load on this rib and see if it's going to work. Well guys, thanks for watching. Till next time.